What's this? Complex numbers? I guess you've heard of a lot of sets of numbers. Real numbers, natural numbers, integers, surds even. But what are complex numbers? Sounds like they might be a bit complex, mate. Small joke. Okay, what I want you to do is look around the screen here. I want you to pause the presentation and try to solve these 4 quadratic equations. There you go. I'm going to stop now and have a go. Well, what'd you find? I guess you see they're colour-coded. Come down here and let's have a go. Did you think to use this formula? Or maybe try to factorise them? Some factorised and some didn't. Oh, we shouldn't have this in here. That shouldn't be in there. Anyway, so maybe you use this formula. What did you actually come up with? Yeah, these two were similar to each other because they had the square root of what we call the discriminant, sometimes abbreviated with a triangle like that, Greek capital D, delta, for discriminant. So here, this was 1, so it meant you can find the b squared take 4ac, sorry, the root of b squared take 4ac was 1, so you could actually solve that. So we would do something like this, -5 plus or minus square root of 1 over 2, which is -5 plus or minus 1 over 2, -4 over 2, or just -2, and -5 take 1, -6 divided by 2 is -3. Okay, so not only was this doable, the square root of 1, it was a perfect square, and I guess this is the same over here. What are we going to do? 1 plus or minus the square root of 25. That's not right. Well, that should have a square root over it, shouldn't it? So square root of 25 over 2, which is 1 plus or minus 5 over 2. So that's 6 over 2, or -4 over 2, and that's going to come to 3, or -2. Some very old work from middle school maths there for the quadratic. So what do you notice? Well, not a problem as long as this thing here is a positive, and if you also have the bonus of it being a perfect square, then it's going to come to rational answers here. And actually the quadratic would have been factorisable. You could have factorised that one. I didn't do that because of the other two. Come down and have a look. Did you get this for those two equations? Here we are. Well, what do you notice? Root b squared take 4ac is the root of -11, and over here it's root of -8. I guess if you've seen this sort of stuff in the past, your teacher would have said, put down no real roots or no solutions. But actually, we're going to look at finding a solution, or creating a solution even maybe, if you want to think about it that way, for this type of problem. So that's where complex numbers is going to come in. And I want to show you something now. Just come down here and I'll just show you this. What if we said, or we imagined, the square root of -1 to be the symbol I? Imagine, so that's what I stands for, an imaginary value, which is the square root of -1. We're now going to define it in that way, whereas previously we've said you can't touch square roots of a negative. What does the problem look like now then? So just come up here a little bit. Oops, hang on too far here. So come down and we'll just put eyes in here now. It's going all over the place. So let's go up here. Okay. Maybe not. Okay. All right, so here we go. X is -3 plus or minus the square root of -11 over 2, which is -3 plus or minus the square root of 11 times -1. Let's break it down. It's all under there. Equals, just come down a little bit. Yep. -3 plus or minus root 11 by root -1 over 2. More room needed. -3 plus or minus root 11I over 2. And we could go a little bit further. Is -3 over 2 plus or minus root 11 over 2I. That got us out of trouble, didn't it? So over here, let's have a look at this one. X equals neg 2 plus or minus the square root of neg 8 over 2, which is neg 2 plus or minus square root of 8 by neg 1 to get neg 8. Neg 2 plus or minus root 8i, which is what, neg 1 plus or minus root 8 over 2i. And we could play with the root 8 as 2 root 2 with your third work. So this is neg 1 plus or minus root 2i. Well, that solved the problem, but it might have created one. These little numbers with i's in them. Okay, let's come down and see what we think. That's the question, isn't it? What is maths coming to, where we define a value that's missing with an imaginary number or a symbol representing, we're imagining the square root of neg 1 is I. What's the point in all of that? Oh, there's some interesting things. Does it lack reality? It's no longer a real number. Can that be practical in any sense in the real world? Or is it just an interesting theoretical branch of mathematics? What we're going to do here in this first presentation is to look at working with them, adding them up, and can you divide them, all that stuff. So it's going to be more or less a pure maths approach. We're looking at the algebra of these numbers. But later on, you'll see that they are of some practical importance. Just for the minute though, I want you to just consider what? Let's multiply this one by, 3. It becomes probably 6 plus 24i. We've got to develop that theory. When we multiply by 3, well, would we times each part by 3? We'd have this. And then if we said, let's perhaps multiply this one by 2, this would be 12 take 24i. And what if we then added these two? What do you notice? Well, we'd have 12 plus 6 is 18. Neg 24i plus 24i would be 0i. We'd be back in real number land. Could that be of use in solving a problem? And still coming up with a practical answer, I'm saying. Oh, interesting, isn't it? You don't have to stay in complex number land if you're starting to work with them. Okay, well, let's come down here, and here's an interesting result. Steinmetz, an American engineer, used complex numbers to solve electrical problems, illustrating that complex numbers did have a practical application, and they used extensively in electronics engineering and science, particularly physics. So it is possible to delve into this area with these numbers and then still come out with a practical answer. Okay, so it's just not a theoretical thing. Let's go down and have a look at developing the theory now. So here we are. Any number of the form a plus bi where a and b are real and I equals square root of neg 1 is called a complex number or an imaginary number. Okay, a complex number that doesn't have a number in front, a real number in front, is called purely imaginary. So we're talking about complex numbers or imaginary numbers consisting of a purely real number here. So this is a real part, and this is a real number as well, but it's called the imaginary part because it is how many imaginaries you've got. Okay, it is a real number as well though. So a and b are both real here. And you can see from the quadratic equation that we did there that, that this is a usual form coming out of that situation. All right, getting some language here. You might like to start to pause the presentation and write down some notes, like the two quadratic equations you tried to solve. I is the square root of neg 1, which means I squared is neg 1, and some of the structure here. All right, let's go on. Interesting bit of algebra now. You might say, oh, well, what have you got here? The sum of two squares. Hey, that doesn't look right. It's a difference of two squares, isn't it? We like this form better to factorise because that comes to a plus b, a take b. But hang on, let's have a look. A squared plus b squared. Now if we call I the square root of -1, here's the result that's interesting. I is the square root of -1, so I squared would be -1. So plus b squared could be written as neg I squared to make that plus. It's a little tricky too, because now we have a squared take b squared I squared, which is a square minus a square. It factors to the first plus the second, first minus the second there. So we can actually factorise the sum of two squares. Here it is here. Just a little summary. So you might like to write that down. So what are we doing? We have, if you like, invented or imagined a solution to this, and now we're going to see what rules might come about for manipulating and using them in an algebraic sense. You've got to have your toolkit all built up. If we're going to go and do it with electronics, we've got to actually understand these numbers and work out what you can do with them, what operations and so on. Okay, so we're building. Here's an example, just a basic use of I equals square root of -1. Thinking of root of -4, it's a root of 4 times -1, which is root 4 by root -1, which is 2i. Square root of -7 is square root of 7 times -1, which is root 7 by root -1. So here, what they're saying is, where you have a root sign, it might pay to put I first. Because if I write this, some people might think it goes over the whole thing. Okay, so you have to be careful there. Write I first to avoid confusion, I by root 7. But usually the form is real part plus imaginary part times I. That is our standard form. And later on, it's going to be very, very important that you always write it that way. All right, in 2A1, so the screen clippings here, as you might have realised, are from Hayes and Harris publications, so you need to have that book handy by there. So let's have a look at you doing some. So I want you to pause the presentation and just do that little exercise. All right, come on down now and let's have a look at the answers. Fairly straightforward idea there. And just have a look there. Just check this, I'm not sure whether you've done this. Root 8 in third work is the root of 4 by 2. Very similar factorisation to what we were doing. Root 4 by root 2, which is 2 root 2. Okay. All right, so just remember you can break that down, and that's third. Third is an expression with a radical or square root sign up. Okay, ready to go on. Let's build up, get some skills here. So here we have some. Rise the product of linear factors, just using the thing again. So this is the sum of two squares. So what are we going to do? We can't do the sum, we want to make that the difference. So it's neg I squared, which would produce a positive there. Okay, so then we have a square minus a square, which is the first plus the second, first minus the second. Over here, plus 11 becomes neg I squared, which is neg 1, which is 1. So it's x squared take 11i squared. First squared minus second squared is first plus second, first minus second. Okay, so I want you to go through every one of these, because it's important to realise now we can factorise in complex number land the sum of two squares. Okay, and just keeping in mind, we can think of 11 as a square because it's the square of root 11. Okay, we did that really in real number theory back in middle school math somewhere. All right, pause the presentation, have a go. Here are the answers now. Let's just check them out that you got all those correct. We can get them all on the screen there. So just go through the theory. It's trying to get you well practiced in the idea that I squared is neg 1. Okay, that's the point there. All right, let's go down now and have a look at some more steps and theory and skills that we can build up here. Okay, solving for x. X squared plus 9 equals 0. you could do it this way by factorising plus or minus 3i, and over on this one, factoring out x squared plus 2, so either x is 0 or x squared take 2i squared is 0, which is that difference of 2 squares, or changing this to a difference first with I squared and then putting each factor equal to 0. Of course, when you get, let's come over here, you could say x squared is -9 and then go x is plus or minus the root of -9, doing it that way without factorising, which is plus or minus 3i. So you could do that. And you could do that also with this part here without factorising. You could say x squared plus 2 equals 0, x squared equals -2, x equals plus or minus root -2 plus or minus root 2i. Okay, so be flexible. I think you should have a go at all of these, do them in a couple of different ways perhaps, and just watch out for the differences. Check these x to the fourths here. Okay, have a look at those. All right, pause it, have a go. Going to show you the answers now. So here they are, down to J. Okay, standard sort of processes there, and then K and L. All right, how are you going? Getting the hang of it? All right, well, let's build it again. Let's build up and see what you think. Okay, example 4 here, back to your ordinary quadratic equation, which is where I thought you might start thinking about the complex numbers to get over that negative discriminant. Okay, so here we are. There's the formula we spoke of before, and just working through here. A is 1, the coefficient of x squared. B is -4, coefficient of x. C is 13. And then substituting carefully in, you can write it all out like this. You get the square root of -36, which is root of 36 by -1, which is root 36i. And you've got a plus or minus out the front. Okay, that idea there of breaking it down. So that means we can solve some of those, all of those quadratic equations where you have a negative discriminant. All right, your turn. Applying the formula to these, you might have to simplify that, clearing the denominator in x there. Okay, pause the presentation and have a go. Come down now and let's have a look at the answers. Okay, A, B, C, D, E and F. Okay, so just check it out, particularly ones which are slightly varying like this one here. All right, let's go. How are you going? Hope you're getting some right here. All right, still in the equation region again, x to the fourth plus x squared is 6. What can you do with this? Well, you know that we try to move all terms to one side equals 0. The reason for that is the null factor law. Right? A product of two factors is 0 or null if one of the factors is null. So we're treating this little one here as a quadratic in x squared. So we're thinking about this as a x squared squared plus b x squared plus c equals 0. Or you could, and therefore you could either do it with a formula or you could factor it like this. X squared by x squared using the old FOIL is x to the fourth. So you're thinking about this as the variable. Right, there it is in there. That is the variable rather than x. And when you've isolated that, you can say either x squared plus 3 is 0, which is going to give you this, or x squared take 2 is 0. So you can put all the factors together and then just put each of them equal to 0 under the null factor law. If a product is 0, one of the factors must be 0 or null. Okay, So getting into those bigger ones now, a bit more algebra there, and really a bit of revision that you can have a quadratic in other powers rather than the single power of the variable. For example, you could have x to the 6 plus x cubed take 6. That would be the same quadratic but in x cubed, wouldn't it? Because it's x cubed squared plus x cubed take 6 equals 0. And you could proceed in the same way, so it's important to be flexible there. So this would be x cubed plus 3 and x cubed take 2. Do you get the idea? We're not going to do those here because we're just going to stay with the power of 4, but this is an expansion of the notion of a quadratic where the variable is not just x. Okay, have a go, and let's look at the answers. Okay, so there's A, B and C. We'll have a look at D. D, E and F. Okay, very good. Let's move on. Now, I promised you that we would look at doing things with them. Now that we have defined the square root of -1 as the imaginary number I, now let's make sure we can do things. So let's keep in mind that both A and B are real numbers. There's the imaginary part. Some students get confused here. The imaginary part of Z is just B, not BI. So A is the real part of Z, written like this. B is the imaginary part of Z. Okay, so there's two real numbers, A and B. It's complex or imaginary number because you've got a real number, lots of I, B times I. Okay, let's try doing addition. What would you say? Well, collecting real parts together and imaginary parts together. As it might be for any algebra work with a pronumeral. I is a pronumeral now standing for the square root of -1. But standing for a number, and we should be able to collect up like terms, if you like. So here A plus BI take C plus DI. Let's subtract the real parts and the imaginary parts. Real parts together, imaginary parts together. That's very important to keep that in mind later on. And then let's do multiplication. We're going to do it with FOIL. We'll do this sort of thing again and write them all out like that. And the real part now, well, they haven't actually tidied this up, but this would be AC take BD, okay, because BDI squared is neg BD, so that's a real part, plus AD plus BC by I. Okay, so that's the idea there, a real part and imaginary part. So when you have actually multiplied that out, the answer here is a complex number and should therefore be written in that form. All right, what about division? Well, it really doesn't make sense to divide something into a complex number of parts, doesn't it? Because really a basic definition of division is to split into equal parts. If you divide by 3, you're splitting it into 3 equal parts or whatever. So what we're going to do here, as you do with surds, and I'll put one down here in a minute, we're going to rationalise or make real, in this case, the denominator, so it becomes a real number. Okay, and the idea here is to use what's called the conjugate. If you use the opposite sign, you multiply out the top line and the bottom line becomes c squared take d squared I squared or c squared plus d squared. So the idea with division is to make the denominator have a real number. Let's go back to something you might have done before, 1 plus root 2 over 1 take root 3. In Surdland, we multiply by the opposite sign to this here, so we're going to create a difference of 2 squares in the bottom line. So 1 plus root 2 by 1 plus root 3. The bottom line is the driver here because we want the first one squared minus the second one squared. And root 3 squared is 3. So that's the idea, and we go on with it from there. So it's really mirroring the idea with surd work there, where you have, let's say, a real number here, which is an integer, and a real number here, which is a surd or an irrational number. So it's a rational part of the number plus an irrational part, because square root of -2, square root of 2 is irrational. So that's the structure of a surd, if you like. Okay, so similar sort of things going on, collecting up the individual parts, rational parts and irrational parts, or in complex number work, the real part and the imaginary part. All right, let's see if you can do some here. So here's an example. We're building up our skills. I hope you're getting excited about that. So here, if z is 3 plus 2i and omega is 4 take I, adding them up, putting them down in full, and then adding the real parts together, collecting those terms, the imaginary parts together. Z take omega 3 plus 2i take, and I'd write it out in full using brackets here, particularly because of that negative sign, and then it's 3 take 4, which is -1, 2i plus I is 3i. All right, so it's the idea of real parts together, imaginary parts together, the product of two, let's write it in full, and then expand it, FOIL, here we go, do each of them, okay, each of the terms, you get this, look at it carefully, because this is positive 2, collecting up the imaginary parts there, -3 and 8, and then we finally write it in the form a plus bi. Okay, well, how's that looking? Let's go down and give you a few to look at. Here's 2a2, there's the first 4. So pause the presentation and have a go. Well, I'll show you the others now. 5, 6 and 7, and then the answers are down below. So pause it again, keep going, or go forward and just check the answers as you go. Here they are now. Okay, 1 and 2. 3 and 4. 5 and 6. And 7. Okay, so we're going well. Let's keep building. So come down now and let's have a look at another example. Getting two complex numbers this time and finding or dividing them. Okay, so dividing them. We look at the bottom line and we convert that to a real number by multiplying by the opposite sign here. It's actually called the conjugate. So when you do that, you'll FOIL out this top line first, outers, inners, last, that sort of rule for expanding a product of two brackets there. And in the bottom line is the crucial line. 4 squared is 16, take I squared. I squared is -1, so that's 17. Okay, and then splitting it into real and imaginary parts. It's customary, but either form will do for that, simplification. Okay, get the idea? Let's go and do it. Let's have a look. Okay, so here's 8, 9 and 10 from that exercise, and it's a matter of just going through and having a go. So pause the presentation, have a go, maybe forward it as you do a couple to make sure you're on the right track. So here are the answers now. Eight and 9, what to B, just check you're working, there's C, and number 10. All right, let's move on and have a look at equating them. So let's have a look at the theorem and the proof. Two complex numbers are equal when their real parts are equal and their imaginary parts are equal. In other words, you can't make this equal to c plus di by having a different number of i's combined with a different number of a's and somehow magically coming to the same number, because these are kept separate, aren't they? So logically you would expect to both parts to be equal, that you can't borrow equality and make a bigger to make it equal to c by making its b bigger or something like that. So we would expect this result. The real parts must be equal and the imaginary parts equal. So we're going to prove this by a contradiction here. If b is not equal to d, let's have a look. So we've got these two complex numbers, so let's collect the imaginary parts over this side. So subtract di, factorise it, the real parts over on the other side. And so what we've got here is, if we solve for I, we've got I, according to this, as c take a over b take d. And so here, and we're saying b take d is not equal to, so you can divide by it, because we're saying b is not equal to d. Now let's have a look at this number. This is a real number. We've said a, b, c and d are all real, where you drop out the i's. This is a real number. So I all of a sudden has become a real divided by a real. And it's not, it's an imaginary number. It's the basic definition of an imaginary number, isn't it? So this is false. So we've got a contradiction there. B cannot, if b is not equal to d, we get something that is false. Therefore b must be equal to d. Okay, so we've just proven that, and you can then say in the same way that a equals c. So therefore, we've just proven it, that's important. All right, so let's have a look at putting complex numbers equal to each other. So here we are. If we've got this product equal to neg I, what's x and y? Okay, well, from the theorem just up there, we want one side to be a complex number equals the other, and then equate real parts and equate imaginary parts. So here we are. The usual way you think about this, if you want an unknown, you divide by this, get it on a side by itself or some rule like that, whatever you've learned. So that would be neg I over 2 take I. And we can use our division process to solve that, so multiplying by 2 plus I on 2 plus I. So the bottom line then becomes 4 take I squared, or 4 plus 1, which is 5. And so we can put real part and imaginary part and equate the reals and the imaginaries, and we've solved for them. That's a pretty traditional way of finding an unknown. So divide by the thing that was times by it and get it by itself. All right, I want you to practice that, and we're going to show you another way in a minute of doing the same thing. Come down here and have a go at these few. Okay, I want you to do all of them here to build up your skills in working with I and expanding brackets and that sort of thing. So pause the presentation and have a go. All right, let's go down and look at the answers then. There's a set of answers. All right, so check that out, finding the unknowns there. All right, let's look at another way of thinking about it. Here's another way of thinking about it. Same idea, and this time expanding this side, expanding it. FOIL first, outers, inners, last, and all that. Okay, collecting that up, I told you before it's going to be important to have real part, imaginary part, and I, and always to write complex numbers in that strict format. Okay, so now we can say x plus 2 is 5, and 2 take x is y, equating real and imaginary parts. Okay, and we can solve it. So that's the idea in this one, not so much dividing through, but by expanding and equating parts. All right, there are yours, 4 of them. Have a go and see what you think. And I'll show you the answers now. Okay, A, B. So we'll look at C and D, and there's C and D. Okay, so a fair bit of work in some of these, and you've got to be careful as you go along. All right, last little bit now is talking about something very important. Here's a Huddy question for you. How can complex roots hide in a real quadratic equation? What am I talking about there? How are they hiding? Well, what we saw before was something like x squared plus 5x, or what can we do? Plus 7 equals 0. And with that one, the discriminant is 25 take 28, so the discriminant is -3, and you're going to get a solution of -5 plus or minus square root of -3 over 2. Okay, so what that means is we do have a pair of complex numbers here, which are the solutions to that equation. And the question is, how did they hide up here? Well, they're all real numbers here. All the coefficients are real in this quadratic equation. That's what it's called, a real quadratic equation. They're all real numbers. How come we couldn't see any eyes in there? I like to say they were hiding, algebraically hiding in that equation. How can complex roots? So let's go down and answer it. Can you see how they are hiding? I wonder if you can. All right, let's have a look at a couple here. All right, and I think you can probably start to see a pattern. Solve that one with these two roots and these two roots for the other one. Okay, what do you notice about those pairs of roots or solutions to those quadratic equations? What must be true for them to hide behind these numbers here? Well, really, there's a 1 there. There's no I there either. They're all real quadratic equations. That's all that's in this course. Okay, so what happened to the I's? Okay, let's come down and look at the theory. You might be thinking about it. You might have thought about it already. I've got a little exercise here for you. You've probably seen this before. If you have the general quadratic equation like that and you divide through by A, then the sum of the roots is neg b over, that's interesting. That 2 shouldn't be there, should it? Neg b over A, and the product of the roots is c over A. Now, have you seen that before? Back in middle school maths somewhere, the sum of the roots and the product of roots are linked to these coefficients. Can you prove it? Okay, I'll give you a hint here. That result of the sum and product of the roots being linked to the coefficients there is a result of this equation. So I want you to take this equation now and work out a general expression for the sum of the roots and the product of the roots. Okay, so pause the presentation and have a go. Now, watch me do it now. So the two roots are neg b plus root b squared take 4ac over 2a, and neg b take root b squared take 4ac over 2a. So the sum would be neg b plus the root of the discriminant over 2a plus neg b take the root of the discriminant over 2a. Just save me writing out b squared take 4ac. So this would be neg b plus root discriminant take b take root of the discriminant over 2a. And so here the root of the discriminant will disappear, and we've got neg 2b over 2a, which is neg b over a, as required after you've done a proof. Okay. All right, so using these roots again now, the product of the roots, it's over this side now, will be neg b plus root of the discriminant over 2a times neg b, take the root of the discriminant over 2a, which will equal, now it'll be all over 4a squared, won't it? This by this, and the top line will be neg b plus the root of the discriminant neg b take. So that's a difference of, is a take b, a plus b, that's going to be a difference of squares, will be the first one squared minus the second one square, the root of the discriminant is the discriminant. So let's work it out. I'll go down, I'm running out of room. This is b squared, neg b all squared, take b squared, take 4ac, which is discriminant, over 4a squared. So b squared take b squared, and then neg by neg is 4ac over 4a squared. Okay, neg by neg is a positive. Cancelling the 4's, cancelling one of the a's there is c on a. So that result comes directly from the formula for the roots of a quadratic. Here it is here. As a consequence of that, when we have this line up here and just a coefficient of 1 for x squared, then the coefficient of x is minus the sum of the roots, and the constant down the end is the product of the roots. So that's a consequence of that. And you should be able to do this sort of proof. Interesting, I wonder if you can derive this general formula for the roots of a quadratic. Could you do that? I think you have to complete the square, don't you, back on the original quadratic equation. So you might like to, being a budding young mathematician, see if you can derive that formula. Okay, let's go on and use some of that and try to answer the question, how are complex roots hiding in a real quadratic equation? So first of all, this sort of pattern that we get out of that formula, a plus bi and a take bi, we're always going to get that, aren't we? So we've got a name for it. It's neg b plus or minus root b squared take 4ac over 2a. So it's going to be some complex number here, neg b plus over here thing, and then neg b minus. So they're always going to have this sort of pattern. Okay, and they're called complex conjugates. Okay, the two with the opposite sign between them. And you've seen that before probably. There's a third, and its conjugate is 1 take root 2. So they're called conjugates also. And so if you call the first one z, then the symbol for the a take bi is z bar. So this is starting to make it very important that you put real and imaginary in that order. It gets confusing if you write it the other way around, because you want to change that sign to a negative to make the conjugate, but you can't play with these. So it gets confusing if you put bi plus a and start to play around with the signs to get the conjugate. Can you see now why the complex roots can hide within the real coefficients of a real quadratic equation, of course, and that's because the sum and product of the conjugates are both real. Okay, from our derivation before, the sum and product are both real. So that's an important result. All right, come down here now and let's do some construction of equations. So if you've got a pair of complex conjugates, then you know the sum of the roots is going to be neg b over a, which is in there, and the sum is therefore neg 2 is 2c, and we'll just put it in there. So we can, if a is 1, x squared minus the sum of the roots by x plus the product equals 0. Okay, because this is neg b over a. If we have taken a out, then it's going to be 1, and the product is c over a. So we've taken a out as a factor, and therefore in such a quadratic equation, minus the sum of the roots, and this is the product of the roots. Okay. Right, so you can memorise that off, but you just work it out in individual cases, I think is easier. So find all quadratic equations with real coefficients, and that is a root. Well, you know from our discussion now, if it's real quadratic, you can't have any i's as coefficients. So you want to wipe out with the other root the I from that one. So 1 take 2i and 1 plus 2i are the only answers here, because you need to have a sum and a product both equal to a real number. So the i's have to disappear, and the only pair of complex numbers that will have that relationship are conjugates. So the sum of the roots is 2, so it's going to be minus 2x. The product of the roots is across these two, 1 take 4i squared, which is 1 plus 4 is 5. There it is there, and so that's the product, and that's minus the sum. So it's quite easy to do that without memorising C and D and using that theorem up there. I would just do it basically saying the sum is the sum of the real parts, and get the 2 and make it negative, and then do the product 1 take 2i squared, 1 plus 2i squared, and get 5. Okay, so then they're unpacking it here, the sum of the roots and the product of the roots. Okay, so there's the result. If it's a 1 in front of x squared there, you've divided through by a, then the coefficient of x is minus the sum, and the constant down the end is the product. Let's use that, and we'll finish up there. Hope you're not getting too tired here. We're getting some skills together for these. So here is 2A4 from Hayes and Harris. I want you to go through and construct the quadratic equations with real coefficients. So we will use the conjugate properties, and that's all that's in this course. We don't do quadratic equations with imaginary coefficients. Conjugate properties to create those real coefficients, so that we've got imaginary roots hiding in a real quadratic equation. You might like to watch this one here, have a think about that one, and see what you come up with. Okay, pause the presentation, have a go, because I'm going to go on and show you the solutions now. Okay, so there's A bar A through E. Check those off. F, G, H. All right. So same stuff every time there. You can put sum like that, and product like that, or just put the word sum and product. All right, so let's do the final example now and have a look. Now, missing coefficients, we can go backwards and find them in this way. Find A and B if root 2 plus I is a root where A and B are real. This is crucial. So how can you have a complex root of a real quadratic equation? Its conjugate must also be a root. So it's root 2 take I, working the sum out, the product out, but the sum of the roots is neg that value, and the product of the roots is here. So don't forget the negative. Coefficient of x for a monic quadratic, that is x squared, coefficient is 1, is minus the sum, and the constant down the end is the product. Okay, so just a variation. Have a look at these. It says be careful here. You might like to look at the solution after and check whether you were careful enough. But what I'd like you to do is pause that. This is the last set. I'll show you the answers in a minute. Have a go. All right, so coming down here, a bit uphill there. Question 2, and I'll just go up here a little bit. Oh, now we're going to come down here. Here we are. 2A, B, and C, and then the one to be careful, D, just watch the situation here where they discuss that. So you might like to talk to that with your class, talk about that with your classmates or the teacher. So here you are, you've got a new set of numbers, and I want to leave you with a question. Which set is bigger, the set of reals or the set of complex numbers? How do they relate to each other? Can you draw a Venn diagram to indicate the relationship of those two sets. Anyway, I'll leave you with that idea, and cheers for now. I'll catch you in further presentations on complex numbers.